In this problem, we have this function g, whose value depends on several quantities, and we want to compute the partial derivative of this function with respect to just w. Before we review partial derivatives, let's review the notation that we used here. So first, x1, t1, x2, t2, these are quantities that you might remember from lecture 1. If you're watching this video before lecture 1, props to you. All you really need to know is that the superscripts here, they do not represent exponentiation. Instead, they're sort of like when you see subscripts, where we have a bunch of x's and a bunch of t's, and the superscript is just telling us which x and which t we are referring to. Second, this quantity on the right-hand side here depends on several quantities, the w's, the b, the t1, x1, t2, x2, but on the left-hand side here, we wrote g of wb, which makes the dependence of the right-hand side on the w and the b clear, more explicit, and kind of hides the dependence of the right-hand side on the x's and t's. And in machine learning and in math in general, we'll sometimes refer to the right-hand side quantity as just g of wb. Sometimes we might want to make the dependence on the x's and t's explicit. And all of these will refer to the same right-hand side quantity. I think this is something that can be really confusing, especially when we think of mathematical symbols as a set of precise rules that must be followed. But I think it's less confusing if we start to think of these mathematical notations as a language that we use to communicate with one another about the ideas that we have in our heads. Sometimes the person we're communicating with needs to be reminded that g depends on w and b. And other times we want to highlight the dependence on the x's and t's, whatever they are. So right now, w, b, x, t, they might not mean anything to you, which is perfect. All we need to know for this problem is that we want to compute this partial derivative. We care about how g changes when w changes a little bit. And what we're going to do is we are going to treat all the other variables here, all the other letters here, as constants and work as if we're taking a normal derivative. So a partial derivative of a function of several variables is its derivative with respect to just one of those variables. And we're going to treat everything else as a constant. All right, time for an example. Let's look at this example. Right here, we want to compute the partial derivative of this function, which I also called g, and we want to compute the partial derivative with respect to w. So what that means is I am going to treat all the other letters that I see here, a, b, all of that, all of them are going to be treated as a constant. So the partial derivative of g with respect to w is well, I see a w squared here, so I need to use the power rule. I see b times w here, so I'm going to write b, and all the other constants do not change when w changes. So here's our partial derivative. If I were to compute the partial derivative of this same g with respect to b, then what I would do is keep all the other terms, including w, treat those as a constant. So here I'm going to have this term is just a constant, this term is just a constant, this term is just a constant. So I've got w plus 1 as my partial derivative.